So before we start talking about the limit definition of the integral, let's go ahead and talk about some formulas we're going to need to help us do that. So these might look fairly innocuous, and they kind of are, but they're going to lead us to a couple things here real quick. So if I want to find, and so just to make sure everyone is familiar with this, what this notation means, this capital sigma here means summation. So this means we're going to add up from I equals 1 to I equals 5, the function 2i plus 3. So ideally, what we're going to do here is we're just going to plug in I equals 1 and get 2 times 1 plus 3. And then we're done with 1. So then we add and we plug in I equals 2. And we're going to get 2 times 2 plus 3. And then we're done with 2. You can wave to her to come on in if she, I feel like I see someone out there. Maybe they're not trying to come in. I don't know. I'm gonna open up the door. You're looking for 21B, you're welcome to come on in. Okay. What's your name?
Juna.
Jenna?
Yeah, Juna.
Juna.
Yeah.
Nice to meet you.
Nice to meet you as well.
So we're just talking about summation notation over here. I'm gonna keep going. I'm gonna do 2 times 3 plus 3, and then 2 times 4 plus 3, and then 2 times 5 plus 3. And although you can certainly add this up relatively easily, the point really isn't knowing what this adds up to. The point is more seeing that we can break this apart into two different things. We can break this apart into the first terms, 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5, like this. 2 times 1 plus 2 plus 3 plus 4 plus 5, and then 3 plus 3 plus 3 plus 3 plus 3. Which we could write as the following summation. 2 times the sum from I equals 1 to 5 of I plus the sum from I equals 1 to 5 of 3. Or in other words, you can break apart summations that have addition or subtraction, and you can also pull constants out in front of summations. So this 2 times I, you can pull the 2 out in front, and this 2i plus 3, you can break apart into the sum of 2i plus the sum of 3. And then you could actually figure out what it adds up to. That's going to be 2 times 15, which is going to be 30, plus 3 plus 3 plus 3 plus 3 plus 3 is 15, which is 45. I would also point out, because we're going to write it down in a second, that when you do the sum of a constant, you're just adding up the constant however many times you are adding things together. So if you're summing from I equals 1 to 5, you're doing 3 plus another 3 plus another 3 plus another 3 plus another 3 5 times. Same idea here. If you're summing from k equals 2 to 4, so I'm going to get, well, let's see, there's nowhere to plug in the k, so I'm just going to get 6 when k equals 2. Plus another 6 when k equals 3. Plus another 6 when k equals 4, and I'm done. So that's going to be 3 times 6, which is 18. And this last part here is kind of a pain. We certainly could break it up. We can definitely break this up into, those should be k's, not i's. They should match. I was using different subscripts there, or indexes, just to kind of point out that you can use I or K or really anything, but standard choices are usually I, K, J for some reason. I don't actually know why, but those are usually pretty typical. And let's see, I'm going to break this up as 3 times the sum from k equals 1 to 5 of k squared minus 2 times the sum from k equals 1 to 5 of k, which is going to end up being, let's see, 3 times 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared minus 2 times 1 plus 2 plus 3 plus 4 plus 5. Now, we're actually going to need, it would be nice to not, like, this is fine for k equals 5 or from k equals 1 to k equals 5. Like, you could totally add 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared and pretty easily get whatever it's equal to. And actually, no, that's fine. You could add it up. I'm sure you can figure it out. It's not a big deal. But what if we wanted to go, instead of from 1 to 5, from 1 to 50? Right? 1 squared plus 2 squared plus 3 squared all the way up to 50 squared is not something we just easily calculate without knowing what the formula is. There definitely is a formula for the sum of the first k integers, of the sum of the squares of the first k integers. In fact, there's a formula for any positive integer power. So you want to add like the sum of the first n cubes, the sum of the first n fourth powers. There is a formula you can find. We're going to talk about a couple of them, and then we'll mention the rest. So let's start off with the easy one. I want to know, instead of what the sum from k equals 1 to 5 of k is, I want to go from k equals 1 to n. And that's going to be 1 plus 2 plus 3 plus 4 plus all the way to n minus 2 plus n minus 1 plus n. And that equals something. Oh, you want to see what I'm writing maybe? Maybe, just maybe. So we want to know what that's equal to. And there's kind of the tried and true way of finding it, but there's also a really, really kind of slick way of finding what this is equal to. So I'm going to show you the slick way, and then we'll do it the tried and true way for the harder one. So here's what we're going to do. We're going to add up two of them. So I'm going to do 2 times the sum from k equals 1 to n of k. And you might just want to wait for a second to write this down. So I'm going to do 1 plus 2 plus 3 plus all the way to n minus 2 plus n minus 1 plus n. Before I write down the next part, this is an easy question. How many terms are written down here? N terms. Okay, and I'm going to add them up again because I want double it, but I'm going to add them in the reverse order. Meaning I'm going to do plus n minus 1 plus n minus 2 plus all the way to 3 plus 2 plus 1. And then we're going to add vertically. What's 1 plus n? Well, easy. It's n plus 1. What's n minus 1 plus 2? N plus 1. What's n minus 2 plus 3? Oh, it's n plus 1 again. All the way to n minus 2 plus 3 plus n minus 1 plus 2 plus n plus 1. Oh, look, I've got a bunch of n plus 1s. How many of them do I have? There's n of them, right? There's n terms. We doubled it, but then we added them together. So that's really going to equal n times n plus 1. But that's double the sum of the first n terms. So if we divide both sides by 2, we can say that the sum from k equals 1 to n of k, which is just 1 plus 2 plus 3 plus all the way to n minus 1 plus n, is equal to half of that. N times n plus 1 over 2. Pretty cool. I think it's really cool. And we're definitely going to use that formula to help us calculate some things in a minute here. I will just point out it totally does work for any example, but specifically, if you go from k equals 1 to 5 of k, which is 1 plus 2 plus 3 plus 4 plus 5, it's equal to, well, let's see, 5 is n, so it's going to be 5 times 5 plus 1 over 2, which is 5 times 6 over 2, which is definitely 15. And that's what we said it was. So it definitely does work, which is kind of neat. Okay, to do the next one for the sum of k squared, we need this formula. We also need a couple other things. So we need that it is definitely true that the sum from k equals 1 to n of just 1, well, you're adding up 1 n times. 1 plus 1 plus 1 plus all the way to another 1 n times is definitely going to give us n. No big surprise there. Okay, now here's the exciting one. We're going to calculate, we want to find the sum from k equals 1 to n of k squared, which is 1 squared plus 2 squared plus 3 squared plus all the way to n minus 1 squared plus n squared. Oh, I forgot there's one other thing we need before we can really do it. Sure. Let me back up for just 1 second because there's one other thing I want to point out. Sure. Yeah, I want that. We're going to need one other idea here. So let's move that to the side for just a second. The other idea we're going to need before we can calculate this is the idea of a telescoping sum. This idea will resurface when you take 21C, by the way. Telescoping sums definitely show up in 21C. So let's say we want to find the sum of something like k equals 1 to 100 of the square root of k plus 1 minus the square root of k. Well, if we start writing out terms, the first term when k equals 1 is the square root of 2 minus the square root of 1. Plus, when k equals 2, the square root of 3 minus the square root of 2. When k equals 3, square root of 4 minus the square root of 3. And we keep going. The last couple terms are going to be square root of 100 minus the square root of 99 and the square root of 101 minus the square root of 100. But if we look here, look a little closer here, so my writing doesn't look quite so terrible. We can see that a lot of things are going to cancel. This positive square root of 2 and this negative square root of 2 cancel out. This positive square root of 3 and this negative square root of 3 cancel out. This positive root 4 and the negative root 4 that would be over here would cancel out. All the way up to the negative root 99 here would cancel out with the positive root 99 that came before it. The positive root 100 would cancel out with the negative root 100 right there. And you end up with just this and this. It's going to equal the square root of 101 minus the square root of 1, which is just minus 1. The reason it's called a telescoping sum is because it's kind of like, like those spyglass telescopes that you extend like this. So you've got all the terms of the telescope, and then they all collapse down to just like the first term and the last term. Kind of neat. That's why it's called a telescoping sum. So we're going to use this idea to help us calculate this other thing over here. And we're going to calculate, well, we're actually not going to start by trying to calculate the thing we want to calculate. We're going to start with this. So we're going to start with, there's a couple different ways to write this. I like to do it this way. The sum from k equals 1 to n of k plus 1 cubed minus k cubed. You probably, well, I don't know, sometimes teachers have you do this, sometimes they don't. It really depends on the teacher. Yeah, what we're actually doing is we're going to calculate this in two different ways. So here's the first way we're going to calculate it. We're going to, that's not one. Yeah, that's fine, sure. I guess that's fine. I usually start this differently, but it's fine. So we're going to write out the terms. We're going to say, well, that's going to be, sorry, I'm going to write down here. So let's see, I'm going to get a 2 cubed minus a 1 cubed, and a 3 cubed minus a 2 cubed, and a 4 cubed minus a 3 cubed, all the way to the last couple terms. I like to at least go to like n minus 1. I don't like to go to just the last term. So I'm going to get an n minus 1 cube, sorry, an n minus 1 plus 1 cubed minus an n minus 1 cubed. And when I plug in n, I'm going to get an n plus 1 cubed minus an n cubed. And so just like the previous example, lots of things cancel. The 2 cubed and the negative 2 cubed cancel. The 3 cubed and the negative 3 cubed cancel. The 4 cubed and the negative 4 cubed. All the way up to the n cubed, negative n cubed, and the positive n cubed. The negative n minus 1 cubed and the positive n minus 1 cubed over there. And that's going to give us, let's see, what do we got here? Negative 1 cubed plus n plus 1 cubed, which we do want to simplify. That's going to be negative 1 plus n cubed plus 3n squared plus 3n plus 1, which is n cubed plus 3n squared plus 3n. So that's one of the things we're going to calculate. The other way we're going to calculate this is we're going to collapse the terms together, meaning we're going to write this as, I'm just going to simplify the insides here and write this as k plus 1 cubed minus k cubed. That's going to be the sum from k equals 1 to n of k cubed plus 3k squared plus 3k plus 1 minus k cubed. And the k cubes cancel. That's going to be the sum from k equals 1 to n of 3k squared plus 3k plus 1. And now here's what we're going to do. We're going to break this into 3 pieces, right? Because we've got 3 things added together. And we just saw that you have the sum of things added together. You can break it apart into different pieces. And we're going to pull out the constants. And then we know most of the things in there except for the sum of k squared. So here's what we're going to get. We're going to get 3 times the sum from k equals 1 to n of k squared plus 3 times the sum from k equals 1 to n of k. By the way, we know, we just showed that that's equal to n times n plus 1 over 2. And we're going to get the sum from k equals 1 to n of k, which we know is equal to just n. So this ends up equaling 3 times the thing we want plus 3 times n plus 1 over 2 plus n. One sec. And these two things are equal to each other. We've calculated the same thing in 2 different ways, which is going to allow us to solve for the thing that we were actually being asked to find, sum of k squared. Oh, thank you. Yeah, sorry. Yeah. So 1, can't you tell? Yeah. Call. So now it's just a little bit of algebra. We're going to set this equal to that and solve for the sum of k squared. Do I have enough room here? Probably not. Let's get this other piece of paper over here. And no, let's not. Let's just, sure. Always running out of room. So solving this, we're going to have, let's see here. 3 times the sum from k equals 1 to n of k squared. And I'm just going to bring, no, that's right here, plus 3 times n plus 1 over 2 plus n equal to n cubed plus 3n squared plus 3n. And I found the easiest way to make this work is just to multiply everything by 2. So multiplying everything by 2, we're going to get 6 times the sum from k equals 1 to n of k squared plus 3 times n plus 1 plus 2n equal to 2n cubed plus 6n squared plus 6n. Now we're going to subtract all this to the other side. So that 6 times the sum from k equals 1 to n of k squared is equal to 2n cubed plus 6n squared plus 6n minus this, which is 3n squared plus 3n minus this. So simplifying, that's going to be 2n cubed. 6n squared minus 3n squared is 3n squared. And 6n minus 3n minus 2n is just an n. And this definitely factors as n times 2n squared plus 3n plus 1, which factors further as n times 2n plus 1 times n plus 1. So we end up getting that the summation from k equal to 1 from 1 to n of k squared is equal to n times 2n plus 1 times n plus 1 divided by 6. It's kind of cool. I mean, okay, it's not bad. Actually, you know what's really cool? Here's what's really cool, in my opinion. We're not going to derive this one. So I should say, you can derive each subsequent one by knowing all the previous ones and doing the same sort of thing. So if you wanted to, I don't recommend it, but if you wanted to find the formula for the sum from k equals 1 to n of k cubed, you would start with the sum from k equals 1 to n of k plus 1 to the 4th minus k to the 4th, and do the same sort of thing we just did. Now here is what's really cool, I think. Sum of the first n cubic numbers is equal to n times n plus 1 over 2 squared. That is, it's equal to the sum of the first n integers quantity squared. I think that's neat. So what I'm really saying here, like for example, is if you took like 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, it is in fact equal to 1 plus 2 plus 3 plus 4 squared, which I think is neat. Okay, that's beside the point. The formula is what we're going to use to help us calculate some of these limit definitions of integrals. We're going to find the area under the curve. So, papers in order here. Yeah, cool. Back to the real problem at hand here. Over here, sure. Yeah. Yeah. Oh, I know. I don't want to hand out something. So, I've got a handout and I'll post it on Canvas as well. So here are the rules we just talked about. The summation is. You don't use them a whole lot in the class, but they do come up a little bit. They definitely come up also in 21C. Maybe not. Oh, okay. So, so let's go on to some examples. So what we're going to want to do here is try to find, we want to find the area under, let's say, f of x equal to x squared on the interval from 1 to 3. And there's a little bit of machinery to build up here. We've talked, so let me actually grab this real quick here. Yeah. So if I wanted to do this, let's talk about how we'd approximate it. If I wanted to approximate this using n equal to 4 rectangles with a regular partition, just meaning each of the intervals has the same width, then the way we would do this would be, let's see, we're going to draw our region here to the left. Like this, 3. And so what we're doing is we're taking this region that we want to find the area of, and we're breaking this apart into 4 subintervals. And so the way we would calculate the area here is, or the way we'd approximate the area is, it'd be the sum from k equals 1 to 4, and each rectangle, which I suppose I should draw here. Oh, I'm sorry, I forgot to give you the attendance form link there. There you go. Each rectangle, if we're going to use right endpoints, for example, would look like this. Those are rectangles, and the way we're calculating the area of those rectangles is base times height. So the base, I should talk about the height first. The height is just your function, f of x equal to x squared, evaluated at some c sub k in the kth interval. So c sub k is a point in the kth interval. The way I've drawn this specifically is using the right endpoint. But you could pick any point. You pick the left endpoint, the midpoint, some other point. Really doesn't matter, because eventually we're going to let things get really, really narrow. And then we're going to multiply that by the base, which is just the difference between your right endpoint x sub k and your left endpoint x sub k minus 1. So here what we've got going on is this first point here. That's your x sub 0. That's your x sub 1. That's your x sub 2. That's your x sub 3. And that's your x sub 4, which is your x sub n, right? Because we're using n equal to 4 rectangles. But as we let n get larger and larger, we're going to have more intervals, and we're going to have more points, or we're going to have a partition of more points. And then we could calculate this. It's not too terrible to calculate. It's going to be the sum from k equals 1 to 4 of, let's see, RC sub k. We're really using x sub k because that is, so there's some notation, interesting things here. People use c sub k to mean any point in the interval, typically. And they use x sub k to specifically mean the right endpoint of an interval. Sometimes people will get that twisted or turned around, but that's usually what people actually mean. So if I'm talking about x sub k is equal to my first point A plus my interval width, assuming it's a regular interval, meaning it's the same width each time, which in this case is 1/2 times the number of times I want to go over. So x sub 1 is 1 plus 1/2. X sub 2 is 1 plus 1/2 times 2. X sub 3, can you see that? No, you can't. is 1 plus 1/2 times 3, and x sub 4 is 1 plus 1/2 times 4. The very kind of general way of writing the right endpoint is that x sub k is equal to a plus delta x times k.
Why does the endpoint matter for the integral?
It doesn't really, except, so here's the thing. In fact, no, I don't actually have that. So the thing is, the integral gets defined very generally, but it's a pain in the butt to calculate. And so even though you can use right endpoint, left endpoint, midpoint, some other point, it is very much the easiest to calculate if you use the right endpoint. That's why we often talk about using the right endpoint.
And that's where the 1 is on the graph.
So let me back up just a little bit here. We're talking about writing the right endpoint. So I should say x sub k is the right endpoint of the kth interval. So for the first interval, the right endpoint is 1 plus 1/2. So we're getting 1 plus 1/2 times 1. For k equals 2 for the second interval, the right endpoint is 1 plus 1/2 plus 1/2. So you're starting here at whatever like your leftmost endpoint is, and then to find the right endpoint, you're just adding on however many subintervals you're going over. So if you're going over 3 subintervals, you're going to add the width of each subinterval 3 times. That's what's happening there. So in this particular case, we're going to get 1 plus 1/2 k squared, because that's our right endpoint. And the function is that we're squaring it. That's going to give us the height of our function times the base, which is 1/2. Each of these rectangles have a base of 1/2. And in this particular example, that's going to end up being 3/2 squared times 1/2 plus 2 squared times 1/2 plus 5/2 squared times 1/2 plus 3 squared times 1/2, which I might have written down, so I don't have to actually think about it again. Sure, that's going to be 1/2 times 9/4 plus 16/4 plus 25/4 plus 9 is 36/4, which ends up being, let's see, 25, 50, 86. 86 over 8, which reduces to 43 over 4, or 10.75. Definitely an overestimate, right? Our rectangles definitely have more area than the actual area under the curve. So the question now is, how do we make our estimate better? And the answer really is use more rectangles. So it's always a race against time to get the so oh, in fact, let me say, yeah. Paper. How do we get a better estimate? We're going to use more rectangles. The idea being that we're going to use an infinite number of rectangles to get an actual exact value or calculation of the area under the curve, meaning we're going to use a limit eventually. So I'll just point out that if we use instead n equals 8 rectangles, I'm going to be kind of a little loosey-goosey with this next one here, we would have something that looked like this. Drawing skills deteriorating quickly here. So we'd have a region that looked like this. Let me break that up into 8 rectangles. So each rectangle is half as wide as it was before. They're going to look like this. Maybe better drawing than I usually do. So here, our approximation would be the sum from n equals 1, sorry, k equals 1 to 8 of, again, the height of each rectangle. So the height of each rectangle is just going to be f of x sub k. Talk about x sub k in a minute. And then the width of each rectangle is going to be 2/8. Because we've got a length of 2 or an interval length of 2 divided by 8 rectangles. So each, our x sub 0 is 1, our x sub 1 is 1 plus 1/4, our x sub 2 is 1 plus 2 times 1/4, and so on and so on and so on. So this ends up equaling the sum from k equals 1 to 8 of 1 plus k times 1/4 to the second power. Let's take a look at that and see if it really makes sense to us for a second. So this first rectangle, that right-hand point, right, the area there is going to be a base of 1/4, and the height we're going to get by plugging in 1 plus 1/4 to the function. And then the second rectangle, base of 1/4, we're going to move over another 1/4 to get 1 plus 2/4 or 6/4 squared. And we're just going to keep repeating that pattern. 1/4 times 7/4 squared, all the way till the very last rectangle. Let's do the second to last rectangle. 1/4 times that one here. This rectangle has a height of, if we plug in, 11/4. And the last one has a height of, if we plug in 3, which is 12/4. If we add those all up, it doesn't really matter. Okay, it matters. We actually add them all up. I think I did it. Let's see if I actually did it. I did. If you add those all up, you get 315/32, which is equal to 9.84375. So definitely a much better estimate in that, right? Our previous estimate was 10.75. This estimate is almost 1 less and it's still an overestimate. So we definitely got closer because it's an overestimate, but it's a much less overestimate. All right. But now we're actually going to do the thing. So we need to have a couple things happen here for this to work. We need actually 2 things. Trying to keep things in order. It's always a story. So actually calculate the area under the curve. We need 2 things to happen. Thing 1, we need an infinite. Oh, wow. That's okay. Come on. We need an infinite number of rectangles. We need the number of rectangles to be as many as possible so that the amount we're off by is very, very, very small. So we need, and to go to infinity. Now, there's actually a little bit more to say about this because you might happen to have a right? So I've always been showing you examples where all the rectangles have the same width because that's usually what people do, but you don't have to do that. You can totally have an example where the partition was irregular and you had rectangles of different widths. So we also need to clarify that we need that all of the largest width of a rectangle has to get smaller, smaller, smaller. So we need the largest width of any subinterval to get small. Or more accurately stated, the norm of the partition. So the norm of this is called the norm of the partition. And it really just means the width of your widest rectangle. The norm of the partition has to go to 0.
Or is it even possible for n to approach infinity and the partition not approaching 0?
Yes.
What shape would that look like?
Here's an example. I'm not going to draw because it's already drawn for me. Here's an example of a region under the square root function where you've defined your partition in a way so that this part here always is looking like this, and all of these are getting smaller, smaller, smaller. So you're having the number of intervals, or the number of subintervals approach infinity, but the norm is not approaching 0 because this particular subinterval always has the same width. And then you're totally going to always be off by this amount here. So that's why we also need the widths of all the subintervals to get smaller and smaller and smaller.
So you can have a fixed interval.
Right. Now, typically it's not an issue because most of the time we're just saying each subinterval has the same width. the total length divided by n, the number of subintervals. So if that's the case, oops, sorry. So if we have those two things, yeah, then here's what we're going to do. So assuming these two things are true, then we are going to define the area under f of x on the interval from a to b as what we do typically call the limiting Riemann sum. And we're going to write it in the following way. So we're going to use the interval notation because that's typical. So all this means right now, even though we've used this to mean antiderivative in the past, forget that. I mean, we're going to come back to it. We've used it because there's a reason. And we're going to say that the area under the curve f of x between a and b is equal to the limit as the norm approaches 0 of the sum from k equals 1 to n of the heights of the rectangles times the width of each subinterval that rectangle came from. Now, the problem with this particularly is it's not very specific. This is saying you can use, right, where I should say C sub k is any point in the subinterval x sub k to x sub k minus 1 to x sub k. So even though we typically define the interval this way or the area under the curve this way, we then usually like to say, well, even though you can pick any point you want over your subinterval, we're going to usually pick the right endpoint and make our subinterval have a regular partition so that we don't have this terrible calculation. So what we're going to actually end up doing is we're going to say, typically, we will actually calculate the limit as your norm goes to 0 of the sum from k equals 1 to n of f of x sub k, where x sub k is the right endpoint, and times the width of each subinterval, which is delta x, where your delta x is the total interval length divided into n pieces. This is the usual way of calculating it. So, yeah, we definitely we have enough time, I promise. So when I do this, what I typically think about doing is saying, I'm going to take my interval, and again, we're trying to calculate the area from 1 to 3 under x squared. I'm going to draw the interval from 1 to 3. I'm not going to worry about drawing the function. I want to find just a way to make this easy to divide up to get the thing I want. So each subinterval, each delta x width is going to be 3 minus 1 over n, which is 2 over n. So each subsequent endpoint is just going to be 2 over n further to the right than the previous one. So here's my x sub 0. And then the next one here, x sub 1 is going to be 1 plus 2 over n. And x sub 2 is going to be 1 plus 2 over n. Sorry, 1 plus 2 times 2 over n. You're welcome. And then x sub 3, same sort of deal. X sub 3 is 1 plus 3 times 2 over n. Each time, we're just adding the delta x to get to the next point. And so I think it becomes not too terrible to see that I'm just multiplying by the next integer. So x sub 4 is going to be 1 plus 4 times 2 over n. So that we can see that if you're over here at the kth subinterval, where the right endpoint is x sub k and the left endpoint is x sub k minus 1, the x sub k is 1 plus k times 2 over n. so that we can then write that our area under the curve from 1 to 3 of x squared dx is going to equal the limit as, now, in this case, we can say that instead of saying that the norm is approaching 0, we know that if n approaches infinity, each of those widths are going to get smaller and smaller and smaller and going to approach 0. So here, the norm approaching 0 is equivalent to n approaching infinity, which is usually going to be the case. It's not very likely that's not the case. Papers, always the papers. And then we're going to have the sum from k equals 1 to n of f of our x sub k, which is 1 plus k times 2 over n, times our delta x, which is 2 over n. And this is where we're going to end up using those formulas that we talked about at the beginning of class. So we're going to write this as the limit as n goes to infinity of the sum from k equals 1 to n of, our function is just x squared. So we're going to get 1 plus 2k over n squared times 2 over n. Depending on the class you're in, you may never actually do this. It wouldn't surprise me if Gorski never talks about this because he usually kind of doesn't. On the other hand, some other people will definitely talk about this. So it's really kind of professor dependent. It's kind of like back in 21A, some people really went hard on the delta epsilon proofs and some people really didn't. So it's kind of the same situation. You might have someone who's really like, I need you to see these details. Someone's like, not so much. I feel like you should see them at least once. So here's what we're going to do with this. We're going to take this limit as n goes to infinity of the sum from k equals 1 to n of 1 plus 2k over n squared times 2 over n. And we're just going to multiply it all out. It's going to work. It's kind of cool to work. Like I always think this works. I'm like, really? This works? Yeah, it works. So if we multiply this out, let's see, 1 plus 2k over n squared, I'm going to get 1 plus 2 times 2k over n plus 2k over n quantity squared, which is 4k squared over n squared times 2 over n. I'm going to distribute the 2 over n and get the limit as n goes to infinity of the sum from k equals 1 to n of 2 over n plus 8k over n squared plus 8k cubed over n cubed, over, 8k squared over n cubed. And here's a sign that you know you're on the right track. If you get to this point and each power of n has a power of k above it that's 1 less, you are on the right track. So I'm happy to see a k squared over n cubed and a k to the first over n squared and a k to the 0th, which isn't there, over n to the first. If that's the case, I'm confident that I'm doing the right thing. So then we're going to break this apart into 3 sums, and we're going to pull out all the constants. And let's do it in 2 steps. So it's the sum from k equals 1 to n of 2 over n, plus the sum from k equals 1 to n of 8k over n squared, plus the sum from k equals 1 to n of 8k squared over n cubed. And as far as each of these summations is concerned, the only thing that isn't a constant is k. K is changing, right? It's increasing every time, 1, 2, 3, etc. But everything else, including the n, is looked at as a constant as far as that summation is concerned. So I'm going to pull out all the constants, meaning I'm going to write this as the limit as n goes to infinity of 2 over n times the sum from k equals 1 to n of 1. And 8 over n squared times the sum from k equals 1 to n of k, plus 8 over n cubed times the sum from k equals 1 to n of k squared. And now, the things that are left inside the summations, we know the formula for those summations. That's what we talked about at the beginning of class. This is equal to the limit as n goes to infinity of 2 over n times the sum from k equals 1 to n of 1 is just n. You're adding up 1 n times. And 8 over n squared times the sum from k equals 1 to n of k is 1 plus 2 plus 3 plus 4 plus all the way to n is n times n plus 1 over 2. And 8 over n cubed, the sum from k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 all over 6. Okay, we're almost done. Here's where I think you can all make a pretty quick leap to the end. You don't have to multiply anything out at this point. Let me ask you a quick question off to the side here. Everybody should be able to think about the answer to this question and think, what's the limit as x goes to infinity of 2x squared plus 5x plus 1 over 7x squared minus 9x plus 3. Think about it for a second. It's a fraction. All right. What is the limit of this rational expression here? Yeah, it's exactly 2/7. You could either use the rule that when you have a rational function and the top and the bottom have the same degree, the limit is the quotient of the leading coefficients, or you could do more work and like use L'Hopital's rule or divide everything by x squared. Either way, you're going to get 2/7. Each of these expressions has the same sort of thing going on. In fact, this one we could just cancel the ends and get 2. But this here, if you did multiply it out, the top would have an 8n squared plus some other stuff, and the bottom would be 2n squared. And the limit of that would be 8 over 2. And similarly here, if you multiplied out the top, you'd have 8 times n times n times 2n. So you'd have an 16n cubed plus some lower terms, and the bottom would be a 6n cubed. And the limit of that would be 16 over 6. So when you get to this stage of this kind of problem, you can just think about, okay, what's the leading coefficient on the top going to be? What's the leading coefficient on the bottom going to be? And those are the coefficients that make up your quotient. And then we can simplify. This is going to be 2 plus 4 plus 8/3, which is 6 plus 8/3, which is, 8 2/3. Or if you prefer, 26/3. And if you are familiar with the fundamental theorem of calculus already, you know that you could have calculated this by doing the antiderivative of x squared. So just as a kind of preview of what you're eventually, or maybe already doing, if you antidifferentiate x squared, you get x cubed over 3. And then if you plug in the endpoints, the top one first, you get 3 cubed over 3 minus 1 cubed over 3, which is 27/3 minus 1/3, which is 26/3. Oh, it's the same. So that's kind of the idea, is that this whole terrible process, which is terrible, eventually we're going to see that you can do this much nicer fundamental theorem of calculus thing to calculate this. Two things. One thing. On the hand that I gave you, there's a backside to it as well. And the backside has another example that goes through all this again, and it looks pretty nice. I didn't write it up, but it's still worthwhile. So you can look at that as well. What I did felt kind of messy or rushed. You can certainly look at this as well. That's it. I think I only had one thing to say. No class on Monday, right? Martin Luther King Day. Don't show up. I won't be here. I'll see you on Wednesday. Yeah. I think that's it.